Will you never marry me? She says, yes, of course. All right, last time we were talking about 5.1 compositions of functions. Composition of functions. So let's do a quick composition of functions, right? F of x is, let's see, 5x over, no, 2x over 5 minus x. That looks familiar. And g of x is 1 over x. And we want to find the domain of f, the domain of g, the domain of h, where h is the composition of f and g. Right? What's the domain of f?
X can't equal 5.
Good. Domain of g?
X can't equal 0.
Nice. If g equals 5, I'm in trouble as well, because g is going to give me an output, which is the input of f, right?
Oh, right.
So I want to make sure that my domain of h is x does not equal 5, or what? What value of x will give me an output of 5 for, an output of 5 for g, sorry.
Half? No. 1 over 5?
Good. So there's my domain of h, and now let's find h as f composed of g of x, and I will be right back. Anybody have an answer?
I guess.
Numerator is?
2 over x.
Numerator is?
2 over x.
Okay. And denominator is?
5 minus 1 over x.
Okay. So we want to have a single factored numerator and a single factored denominator. So again, watch me do this. I have a 2 times x over 5 minus 5 minus x, empty parens, and I'm putting in my other function. So I agree with what you have, but then I want to get rid of my interior denominators, right? So I'm going to clear fractions with an LCD, just like I did in the difference quotient, right? So I get 2 over 5x minus 1, and there's my function. There is my composition. So yes, I agree with your start, but we want to keep going. And this is something that happens in calculus all the time. We think we're done, but then we look at the answer and it's nothing like what we have, and then it's usually factoring. Or it's definitely algebra. So on this one, we are interested in a couple of different inputs. So for example, 2 looks fine, right? So let's find g of 2. So g of 2 is 1/2, and from there I want to find f of 1/2, right? So f of 1/2 is 2 times 1/2 over 5 minus 1/2. And again, where did I get this from? I just picked something in the domain, right? So what do I get? I get 1 over, don't tell me, 9/2, which is 2/9. And now I want to see what happens when I put into h, right? So h of 2, notice, is 2 over 5 times 2 minus 1. That's 2 over 10 minus 1, which is 2 over 9. Same answer. someone wrote in the chat, sorry we let you down. You didn't let me down. Yeah, I want you all to succeed, and if there's something you think I could do better, I want to do better. Right? About talking about the grades in the class right now. But definitely we need more work. All right, so there's our composition of functions that we talked about last time. Of course, if I ask you for a composition, I am going to be asking you for compositions of functions, usually to show that I have an inverse function. So let's get started on section 5.2 here. 5.2, we're talking about one-to-one functions. And inverse functions. I think we started it, but I felt like maybe it was a little rushed. You know, that Monday before the second test. So just make sure I go over everything again. Hold on, someone's knocking at my door. And just, I'm teaching right now, so don't worry about. Okay, thanks. What a day! What a day, repairman. Okay, sorry about that. So one-to-one functions and inverse. It's tough to work from home and learn from home and teach from home because there's all these distractions. One of the things that really helped me when I was a student was working in the library, right? I didn't have a TV. I didn't have a fridge filled with cold beer, right? Didn't have phone. No phone when there was not even a flip phone yet. So notice if you can cut out the distractions, it's a lot easier to study. So anyway, we say a function is one-to-one if f of a equals f of b implies a equals b. And so the way I say that as a human is if there are no repeated outputs. The way we're usually used to hearing it is for every unique y there was one and only one x. For every unique y there is one and only one x. And you've heard that language before, am I right? Have you heard something like this before? Have you heard something like this before in our mathematical lives? Have you heard something like that before?
Yes.
Yes, Grace. Where have you heard it before?
When you had started teaching topic 2.
Exactly, with the functions. So we said if I have something, it's a function if for every x, for every unique x, right? There's one and only one y. And now we're switching the two, which is a big hint that where we're going here, switching inputs and outputs. So now all of a sudden I'm saying for every output, I used to say for every input there's only one output, right? Remember the soda machine with the chicken, right? So for every output now, I can only have one input, right? So another way of saying this, a function is one-to-one if the graph passes the horizontal line test. When we needed it to be a function, it was a vertical line test, right? But if I switch x's and y's, it's hard to realize it but that vertical line becomes a horizontal line. A function is one-to-one if the graph passes the horizontal line test. So for example, y equals x squared is not one-to-one, right? Because x squared fails the horizontal line test, right? If I have this height here and the same height here, I have a repeated height. I cannot have a repeated height in order for it to be one-to-one. Y equals e to the x is one-to-one. We're about to learn about this function e to the x. But anywhere I draw my horizontal line, it hits only once. So for every unique height, there's only one x value. No repeated y values. Our big thing is, if a function is one-to-one, then the inverse exists, right? So this is the important piece. If f is one-to-one, then f inverse, which I'll often call g, exists. If f of x is a one-to-one function, then the inverse function, this should be f to the minus 1, f inverse, that's how it's read. Right? F to the minus 1 of x is read f inverse. So that -1 doesn't mean -1. It doesn't mean reciprocal. It means inverse. Okay. So if f of x is one-to-one, then the inverse function, which I like to call g of x so I don't have to write so much, exists. And so then we would like to be able to find inverse functions, right? So so that's what we want to be able to do here. We want to find inverse functions. Show that f of x equals 2x minus 1 is one-to-one, and then find the inverse. Demonstrate that f composed of f inverse equals f inverse composed of f equals x. What happens when I compose a function with its inverse is everything falls apart, because the two functions undo each other. That's what an inverse function does. I used to think that, so think of a machine that I put $1 in and out comes a soda, right? But then I wanted, oh my God, I forgot I have to take the bus. So I put the soda back in, I put the soda in the inverse machine and out comes $1 back, right? Of course, I shake up the soda first. But anyway, I used to think when I was putting my $1 in and it would just keep coming back out, right? Some people would think it's too wrinkly, but I really know the truth. I'm putting my $1 in inside the machine, it changes it to a soda. But inside of that machine is also the inverse, so it takes the soda, gets $1 back, and then that's what comes out of the machine. So it's not the dollar is too wrinkled. It's that there's a composition of a function and its inverse there, right? I put it in, I get a soda. I put the soda back in, I get the $1. And that's what I want. I want everything to fall apart, right? So when I compose a function with its inverse, I get what I originally started with. I get that original input. Okay. So here we go. Show f of a equals f of b implies a equals b, right? So since I have the same output, I better have the same input, right? That's what it's saying. So 2a minus 1 should equal 2b minus 1. I'm going to add 1 to everything. I get 2a equals 2b. And I'm going to divide by 2, and I get a equals b. So f is 1 to 1. Everyone okay?
Yeah.
Nice. Now I know, since f is 1 to 1, the inverse exists. Okay? So I want to find f inverse. And I might as well call it g, because it's a lot easier to write. So what I do is I start with f of x.
Sorry, Professor, could
Yes.
you show the a is equal to b, but with a excuse me, but with a function that's not 1 to 1?
Yes. Well, no.
X
Then
squared.
a won't be b. Yeah. So that's
Yeah. So
that's
could you show how it won't be b?
Yes.
I'm a little confused.
sure. Y equals x squared is not 1 to 1. So a squared equal b squared should not imply that a equals b. Right? It'll be false. Well, square root both sides. I get square root of a squared equals plus or minus square root of b squared. So I get a equals plus or minus b. It's not equal b. It's either equal to b or minus b. The negative b.
Okay.
Yeah.
Got it.
Good question. So f is 1 to 1 means my inverse exists. So here's my process. I'm gonna replace y for f of x. So I get y equals 2x minus 1. I'm going to solve for x. So I get y plus 1 equals 2x. So I get x equals y plus 1 over 2. Switch x and y. This is the big reveal. When I'm getting inverse functions, I'm switching my domain and ranges. So I get y equals x plus 1 all over 2. Rename y as f inverse of x. And for us, that's g of x. My process is the same. My process is the same, but the algebra gets more complicated, right? And we'll do one that's very complicated in a second. So I got my function, shown it was 1 to 1, found the inverse function, and now I want to compose them. But before I compose them, let me just show you my domain and range get switched. Okay? So give me a good value to plug in for the original f. Give me something in the domain of f. Remember, f was, what was it, 2x minus 1? Give me a value that's in the domain of f.
5?
Sure. So f of 5 gives me 2 times 5 minus 1. That's 10 minus 1. That's 9. So my input was 5. My output was 9. Right? My input was money. My output was soda. But I want to get my money back. So I want to go to g and put 9 in. So g is 9 plus 1 all over 2. That's 10 over 2, and that's 5. So my domain and range switch. The inputs become outputs and vice versa. This is not enough to prove that I have inverse functions. What I have to do to prove them is do the composition. F composed with g should be equal to x, which should be g composed of f. So both functions, when I compose the two different compositions, they should fall apart. And all I get left with is the original input, which is x. Right? So let's do that. Let's do f composed of g. Well, f is 2 times x minus 1, but g is x plus 1 all over 2. And of course, the 2's will cancel. And I get x plus 1 minus 1, and I get x. Good, that's what I wanted, right? F composed of g should be x. G composed of f should also be x. So let's do that. G composed of f. Everybody with me?
Yeah.
Thank you.
And just one question.
Yes,
Yes,
Diego.
That example when x equals 5, that's not a 1-to-1, right? Because it equals 9.
So in order to be talking about one-to-one pieces, I have to put in different x's to make sure I get different y's. And in this case, I just put in one x. I just said, hey, what's something in the domain? Let's see what happens. Right?
Okay. Yes.
Right. So g composed of f, I have x plus 1 all over 2, but inside of that, I'm putting in my 2x minus 1. And of course, the 1's will cancel, and then the 2's will cancel. And I get x again. And that's what I want. I want my original input back. Whatever I put in, if it goes through this function, inverse function, I get whatever I started with back.
Okay.
This is me putting the dollar in the soda machine, and the dollar comes right back, right? But inside, it gets turned into a soda, and then the soda gets turned back to the dollar, and then the dollar comes out. I don't even think we use dollar bills to pay for soda anymore. And we shouldn't be drinking soda anyway, right?
Yep, I agree. Soda not healthy.
Nope, not good. If I could, I would have trained myself off of sugar. That's what I wish I had done early. Now I'm a diabetic. I overdid it. All right, let's do another one. Let's do something that's more complicated, right? Let's do y equals 5. Let's do the one from the test. 2x minus over 5 minus x. You can tell that this one is 1-to-1. What's this horizontal asymptote?
Horizontal asymptote?
Yes. Long run behavior.
Would it be? I'm just going with
1.
Negative 1. Right. Look at the mother of the numerator and the mother of the denominator. It's not negative 1. It's negative 2. Robert, silly boy. I'm just going to cheat. Negative 2, right?
Okay.
Look at the mother of the numerator, 2x. What's the mother of the denominator?
Yeah.
Negative x. What's the
Negative
ratio?
x.
So negative 2. What's my vertical asymptote?
5.
5.
Oh, 5.
Yeah, 5. Yeah, 5.
Yeah.
Oh, okay, I got it.
What is an intercept for me?
Yeah, 0, 0.
0, 0. Very, very good. What's the short run at 5?
Oh, that's
it. It's a whole.
Yeah, no, it's an asymptote,
But I'm going to plug it in where I can. So I get 2
Yeah.
times 5 over 5 minus x. So I get a 10 over 5 minus x. So it kind of looks like negative 1 over x. So I got to be down here and up here, which makes sense because I had to go through that red point. you think you're going to see any of this old stuff on the next exam? You're going to see any of this kind of stuff on the next exam? Anybody have an idea?
Probably. Most likely.
Definitely. You're going to see any of this stuff in calculus? All of it.
Definitely.
All of it. And more. It's not going to go away. You can't hide from it. You can only, stand the pain of a toothache long enough until you're going to have to pull it out yourself if there's no dentist. You can't hide from this. You can't just ignore this stuff. It's not going to go away. Can you tell right away that this thing is 1-to-1?
Yeah, because they don't have any of the same heights.
Exactly. It passes the horizontal line test. No matter where I draw a horizontal line, it only hits one height at any time. Right? And I'm kind of pretending I'm dragging that horizontal line. Can I do that with this stupid, can I do that? No. How can I do that? Can I just grab it? No, I can't. I'm trying to grab the line with my mouse, but I can't. Maybe I can. I'll think about it. So it's clear that it's 1-to-1, but we should be able to show it's 1-to-1. So what I want to do is show that f of a, which is 2a over 5 minus x, equal to f of b, 2a over 5 minus a, 2b over 5 minus b, implies that a equals b. And then I know for sure, right? Then I know for sure. So what do I have? 2a over 5 minus a equals 2b over 5 minus b. Anybody like fractions? Yes, I have a half brother. You can't hate him. But I want to get rid of them, right? Cross multiply. Yes, cross multiply. So I get 2a times 5 minus b equals 2b times 5 minus a. And I don't know what they're talking about inside that room there, but I'd like to disassociate it. I want to distribute, right? I want to get rid of that associative property that's happening. So what do I get? I get 10a minus 2ab is equal to 10b minus 2ab. Oh, well, I've got two ABs on both sides, so they cancel. So I've got 10A equals 10B. So I've got A equals B. Done. 1-to-1. How are we doing?
Good so far.
Nice. Now, what do I want to do? I want to find the inverse function. I want to find the undoing machine. I'm going to test these two machines with something in the input, see that the output and input change, and then I want to compose the functions and show that everything falls apart and all I am left with is the original input, which is x. So I start with y equals 2x over 5 minus x, and I solve for
solve for x and then you switch
solve for x. So I'm going to cross multiply here.
Yes.
I'm going to distribute. When I isolate for x, I would like to do so with the minimum number of negative signs. So meaning if I move the 2x to the left and the 5y to the right, I'd have 3 negative signs. If I move the xy to the right, I have no negative signs. That's what I want. I want the minimum number of negative signs. Everybody okay here? Remember what I'm doing. I'm solving for x. So I get 5y equals x times 2 plus y. Or I get x equals 5y over y plus 2. I just switch the order because it's more of the norm. And now I switch my x and y, so y is equal to 5x over x plus 2. And there's my inverse function, f inverse, which I'm going to call g, because I don't want to write all of that notation all the time. Somewhere on the paper, I want to say that f inverse is g, right?
So this is the inverse function?
This is what I think is the inverse function. I'm going to do I'm going to do a cheap check, and then I'm going to do the most sophisticated check I can. Composing a function with its inverse will return me back to the original input x.
Okay.
Right? So let's pick something in the domain of f, the original function f. What was f again? F was 2x over 5 minus x. Give me something in that domain.
4.
Sure, 4. Nice. So f of 4 turns out to be 2 times 4 over 5 minus 4. So 8. Nice. So when I put in a 4 into my machine, out came an 8. Right? And so what happens?
So when you put an 8,
I want to put an 8 into
GX,
G.
that's
Yes,
one.
exactly. 5 times 8 over 8 plus 2. Oh, that's 40 over 10. That's 4. Inputs and outputs switched. I think I got the inverse. I think I got it. I can't check every input output, right? It'll take forever. So I got to have some way to do it in general to see if I just put one function inside the other, does everything fall apart, right? Like when I put a square inside of a square root, the square root and the square go away, don't they? Right? If I put a square root of 4, isn't that the square root of 2 squared? And the square root and the square go away, right? This is the idea. Everything goes away except for my original input. I started with something squared. I put it in the inverse machine of square root. Then the squaring and the square rooting went away, and I was left with the original 2. So let's see what happens here now as I do f composed of g first. So you're doing this along with me at home or wherever you are. I'm going to write my original function, which was 2 times x all over 5 minus x. And inside of that, I'm putting in my inverse machine, which is, what, 5x over x plus 2. And simplify it. Go. On your mark, it said go. Yes, that's what we wanted to happen.
And Professor, can you just explain again when you switch y and x, when it was 5y equals x?
Yeah, up here.
In this example.
Up here, right?
Yes.
So I started with y equal. I got it to say x equal. And then I'm switching, because I want to write it as a function of x. I don't want it as a function of y. So it's just like naming your kid something. You can name your kid whatever you want, right? Oh, well, almost. But, so right? You could, so I just decided, but remember what's really happening is I'm starting with a certain input, I get an output, then I want to get back to that input. So I've got to switch my x's and y's. Got to switch.
So I see, you divided the y plus 2, x.
Yes.
Okay.
I got it now. You weren't asking about the theory. You were asking, right, what was actually happening.
Yeah.
I got it. All right, do the other composition for me. G composed of f. Go ahead, do that. We already know the answer should be x. But you do it real quick, please. How we do? We get it? Anybody?
Sorry, I'm still working on that.
No problem.
Yes, we got it. It's X.
Nice. Beautiful. So it's telling us something about the graph of a function and its inverse, is that all of the x's and y's trade places, right? Let's take a look at it on Desmos real quick. So let's see, we had our original function y equals 2x all divided by 5 minus x. And that one's in red. And we got our inverse function of 5x, sorry, y equals 5x. Help remind me, over what? X plus 2?
5x.
X plus 2?
5x over x plus 2.
Yeah, thank you. And there's my inverse function. And I want you to notice the symmetry on that 45-degree angle. Do you see the symmetry? So what I'm going to type in here is y equals x, because that is me switching x and y, right? So what point did we pick already? Did we pick? We picked 8.
4.
8. 4. We picked 8. 4 originally, right? So we had the point 4 comma 8, right, on f. Sorry, 4 comma 8, Robert. There's 4 comma 8 on the original function, red function f. And let's see where 8, 4 happens, right? What do you know? What do you know? Look at where they are, right across from each other across that line y equals x, right? Across that line y equals x. 2, 4, 6.
Are they a reflection of the y?
Exactly, because what happens in a function and its inverse? I switch the x and y. So the 4, 8 become 8, 4. Right? And so it reflects across that line y equals x. That y equals x is the mirror of the function and its inverse.
Oh, okay. I got it.
So this is a big hint at drawing a function's inverse. All I have to be able to do is reflect it across that one line. Right? I just have to be able to reflect it across the one line. That line y equals x. It turns out that the very next set of functions that we're going to be learning are inverse functions of each other. And those functions are an exponential function and a logarithmic function. So I want to move on. And we're talking about 5.3 and 5.4 all at once. And you'll see this process for finding inverses is going to happen quite a bit. Switch x, right? Solve for x, switch x and y, rename it, that type of thing. So it's something. It's a process that you will definitely have to do on the next test. Go ahead, Diego.
No, nothing.
No problem. So I want to look at two pretty famous a famous pair of functions, and that is f of x equals e to the x and f inverse of x, or g of x, equals ln of x. So we know this number e, right? E on your calculator, e is approximately, where's my calculator? Oh, sorry. On your calculator, E. Calculator says about 2.718281828. It actually looks like there's a pattern, but there isn't. It's a never-ending, non-repeating decimal. It's a irrational number. It's also called a transcendental number. But usually we'll say E is about 2.72. So this is a number in finance as famous as pi is to circles. As pi goes to geometry, E goes to finance and investing, things like that. So e to the x is our base. And these two functions are inverse of each other. And so we certainly can graph e to the x, right? At x is 0, I get 1. At x is 1, I get e. Right? And so there's my exponential function. Of course, e to any power is never negative, right? A positive number to any power is never negative. A positive number to any power is never 0, right? So we can see this horizontal asymptote of y equals 0, right? Now, what's nice about this is without even doing any work at all, I know, how did I find 0, 1? So I'm just doing f of 0 is e to the 0. Anything raised to the 0 is 1. So 0, 1. Right? So there's my e to the x. And if I just reflect a couple of points, so for example, 1, 0 and e 1, I get a pretty good picture of my ln y equals ln of x. And again, you can see that symmetry, right? You can actually see the cooling towers. If you rotated your paper 45 degrees, right, you see the cooling tower, nuclear cool, right where Homer Simpson works. This turns out to be a conic section, which is chapter 10. I'm hoping we get to chapter 10, but I don't know. Go ahead, Onel.
Oh, no, sorry. I accidentally unmuted.
No problem. So notice that the original function has a horizontal asymptote, right? Horizontal asymptote. Look at the inverse function has a vertical asymptote, right? So all horizontal asymptotes are going to become vertical asymptotes from function to inverse function. Why is that? Because I'm switching x and y. If I switch x and y, how much do I rotate by?
Uh, 180, is it?
300.
I know you
90.
reflect over the
90. 90. But it's a weird kind of 90. Okay, here, let's see if I can show you this. It's a weird kind of 90. I think I can show it. I'm using a Sharpie, so I'm hoping it goes through. I think I can show you. All right, there's my XY axis, right? Yes, you with me? If I rotate just by 90, do you see my Y axis is on the wrong side? Right, if I start from the original, right? I want my X-axis, the positive X-axis, and I think things might be switched for you, but right, you can see my positive X-axis, yes? And my positive Y-axis.
Yeah, I see them.
Okay, if I just rotate 90, do you see my positive, my new X is pointing in the opposite direction. So not only do I have to rotate, I have to spin it. And now I have my positive Y in the same direction as I had before, positive X. So I'm not only rotating 90, right? I'm rotating 90 and then I'm flipping it over. And this is a kind of a interesting concept to be able to visualize when you go to Calc 3 for the engineers here. For all the engineers, not the computer scientists. When you start thinking about higher dimensions, anytime you're shifting, anytime you're rotating, you're also rotating. Once you get to 3 dimensions and higher. So anyway, so you can do homework 5.1 and 5.2 now. Of course, you can do all of the older homework, right? I think we did enough today. A couple of you want to talk to me, so I'll stick around. Now, if you want to speak to me in private, let me take care of everybody else that wants to ask anything in general, and then otherwise I'll see you on Wednesday.
And can you just when will